Welcome to the MH2801 video segment on the scaling property of the Dirac delta function. Now let us recall that the Dirac delta function as a distribution is defined by two conditions. The first of which is the normalization condition, and that states that the integral from minus infinity to infinity of the Dirac delta function delta t minus t naught integrated with respect to time is equals to 1. So this is the normalization condition. Now the other defining characteristic of the Dirac delta function is the localization condition, and that tells us that if we integrate from minus infinity to infinity, f of t multiplied by the Dirac delta function integrated with respect to t, this will give us f at t naught, where t naught is the in the argument of the Dirac delta function. Okay. Now, what about an integral that looks like this? So let's say we have an integral from minus infinity to infinity. Okay, f of t, no problem. We still have f of t, but instead of delta t minus t naught, now we have delta a times t minus t naught. That is, the argument t minus t naught is scaled first by the factor a before you integrate over the Dirac delta function. Now what does this give us? Does this give us f of a t naught? The answer is no. So in order to understand why this is not the case, let us perform a change of variable. So let's say that we change to red color first. So before we do a change of variable, we do a change of pen color. So let u equals to a t minus t naught. Then surely du is equals to a dt, or dt is equals to du over a. Okay, so for now, let's assume that a is greater than 0. Okay, now if a is greater than 0, then when t is equals to minus infinity, what you have is that u is also equals to minus infinity. When t is equals to plus infinity, then so is u. Okay, plus infinity. And then what we need to do next would be to write t in terms of u. So t, because u is a times t minus t naught, t will be equals to t naught plus u divided by a. So now we're ready to evaluate the integral. So let's write down the integral, minus infinity to infinity, f of t naught plus u over a. And then next, what do you have? Next we have delta of u, and then dt is du over a. So if we put all those together, we get 1 over a, an integral from minus infinity to infinity. Okay, f of t naught plus u over a, and then delta u, which we are going to write as u minus 0 du. Okay, now why do we write the argument of the Dirac delta function as u minus 0? Because this is the value that is going to go into here when we integrate over u. And when if we do that, because we just substitute 0 in here, so substitute 0 into u here, what we will get is f of t naught. So what in the end we get 1 over a f of t naught. Now what happens if a is negative? So let's see. If a is negative, so if a is less than 0, we can still write u equals to a t minus t naught, in which case du is still equals to a dt, and therefore dt is still du over a. And in fact, now if we write down t in terms of u, it will still again be t equals to t naught plus u divided by a. The only difference is in the limits. So when t is equals to minus infinity, now because minus infinity is so much bigger than, smaller than minus t naught, this whole thing is of course just minus infinity, but multiplied by a negative constant gives us positive infinity. So positive infinity here, and then of course the same is true on the other side. So when t is equals to plus infinity, we have plus infinity here, but a is negative, so multiply by a negative number gives us u equals to minus infinity. So let's put all those together. We will find that the integral from minus infinity to infinity of f of t delta of a t minus t naught for a negative dt is equals to, okay, the integral from positive infinity to negative infinity, okay, f of t naught, okay, plus u over a, okay, multiplied by delta u minus 0, and then here we have du over a. Now the integration limit obviously looks funny, but we can fix that. We can fix that by observing that a, because it's a negative number, it is actually equals to minus the absolute value of a. Okay, and then we can do the same thing for the argument of the function f, and then we make use of this minus sign to switch the order of the integration limits. So we end up starting from minus infinity and ending up at plus infinity of f t naught minus u over the absolute value of a times delta u minus 0 of du over the absolute value of a. Now when we, okay, let me bring out the 1 over absolute value of a, and now we will have minus infinity plus infinity f of t naught minus u over the absolute value of a times delta u minus 0 du. So what will happen is that when we evaluate this integral, the 0 will be substituted in for u, and therefore we end up with 1 over the absolute value of f t naught. Okay, so we can combine the results for the case of a greater than 0 and a less than 0 as such that, the integral of minus infinity to infinity of f t delta a t minus t naught dt is equals to f t naught divided by the absolute value of a. So when a is positive, the absolute value of a is just itself. When a is negative, the absolute value of a is, of course, just the positive number that you get by taking the absolute value. So this is the scaling property of the Dirac delta function, and it appears that this integral suggests that we can treat delta of a times t minus t0 somewhat like delta t minus t0 divided by the absolute value of a. So this is the scaling property of the Dirac delta function.